rotational transformation. And we kind of gave a formula. And you're going to see this same formula appears in various ways again and again. And at the moment, it doesn't make maybe much sense, but we figure out how to change the coordinates so we can move a point by theta degrees counterclockwise. That we had in the last meeting. If you didn't get it, you will get it in various ways today. Right. Rotating it, what is the x point of the p translated by theta? Remember, the thought was I take a point whose angle right now is theta. I add, whose angle right now is something that only the point knows. I don't care. I don't really use it, but it's nice in the beautiful animation. There is some angle phi that the original point creates with the x-axis. To this point phi, I'm adding the angle theta, which is the angle by which I want to rotate each and every of the points. So what will be the x-coordinate of the new point? The x-coordinate of the new point would be the length of the segment, which we decide is 1, times cosine, but cosine of what? Phi plus theta. So cosine phi plus theta, and cosine phi plus theta, we have a formula for it. Cosine phi plus theta is cosine phi, cosine theta, minus sinus phi, sinus theta. And that's independent of where is the point P actually lies. But now I realize that if P cosine phi is nothing but the projection of P on the x-axis, also known as the x-coordinate of P, what we called A, and similarly for B. So we have now a formula that says the new x is just the old x times cosine theta minus the new the old y times sinus theta. And similarly for the x-axis. We talked about a few other transformation, like reflection by the x-axis. We will take x and y, keep x the same, y is not changed. And we mentioned the old joke with a mathematician that we are trying to recycle solution to problems that we already know how to solve. If we are facing by a new problem, we will try to use solutions to old problem, even if the whole scenario doesn't necessarily make it simpler. Namely, I want to rotate the house around its corner. If I rotate it right now, it will rotate, but not around its corner. It will rotate. The house will move from here to here, which I don't want. I want to keep the house where it is, just rotate it somewhere around P. How would I do it? By a sequence of steps, translate the whole space, that is, add minus P to each and every point in the house. By doing so, the corner of the house will coincide with the origin, xy. Rotate by theta. Now it's legit to rotate. By the way, it's rotation clockwise now, so it's actually rotate by minus theta if I don't tell you which direction to rotate, and the default, if I tell you rotate by theta, is rotate counterclockwise. In this little picture, it's rotating clockwise, so it's rotation by minus theta. And shift it back, so P is right here. That's if you want to be more systematic, which I actually suggest to do, and actually in the homework there is 5 point bonus if you use matrices to do all the operations. You don't have to, but for this we need to tell you how to use matrices for all the operations, what would be the systematic nice one. Reflection, we discussed this one. If I want to reflect the house now around the line which is not the x-axis, again, express it as a sequence of simple steps. translate the house translate the house shift by minus b. What is b? The point where this line meets the y-axis. Translate by 0 minus b. So now the line that I want to reflect by will coincide with the origin. Rotate by the angle alpha. Rotate by alpha. Rotate actually in this case by minus alpha. Why minus alpha? Because it's rotating clockwise. After these two operations, the house is nicely placed right here, above the x-axis. Now you know how to reflect it by the x-axis. We saw it 2 slides ago. Take xy to x minus y. And now do the reverse of these operations. Do the reverse sequence of these operations. That is, I ended by rotating by minus alpha. My next step will be rotate by alpha. The order matters. I started, the first one was shifting by minus b. Now shift by positive b. So we are putting the line. The only change is that this line is still in the same place. And this very strange approach of dividing it into step by step will make sense, but and you'll never need to. It will make sense, and there is a reason that the whole graphic world, as much as I know, followed the same mechanism of let's break it into such tedious but sequence of basic steps. So what stands behind all of it is that we have a lot of points, and when we look at all these points, we want to express one matrix M that does the transformation for us. And M will do the transformations that I want to do, which might be rotation or translation or the product of all this sequence of possibly many rotation, translation, rotation, translation. It will be multiplication by a simple matrix that is that after all this transformation, I will multiply this matrix by P1, and I'll multiply the matrix by P2, all the way up to multiply the matrix by PM. Well, all these points or all these features are part of a very, very complicated geometric scene. Now, why do I say that M might represent sequence of translation operation and so on? Well, what we saw in the previous slide is a simple example, but what happens if I want to determine what is a angle or what is the location and orientation of the last piece of my finger? And to represent the last piece of my finger, I need to tell you what is the angle of this joint times the angle, the length of this part of the arm times the angle over here times the angles over here, and that's a sequence of translation and rotations that eventually tells me what's happening in the last part of the finger as a result of the translation over rotation of all the pieces of the arms. And still at the end, it will end up by a single matrix that I'll multiply by everything. So that's one reason that we like matrices. Like might be a strong word, but that we'll use matrices. And another reason is that our hardware is optimized to death to do multiplication by matrices, and interpolation by matrices, and multiplication by coefficients, and to do it in parallel as much as it could. Even for a single CPU, especially if it has few cores, and much more if you have a piece of hardware that is generated for graphical scenes, namely GPU. Here is a multiplication matrix. I want to know the point AB. Where is this going to? Here is rotation counterclockwise by theta. The new AB, the new location of AB, that is x prime, y prime, would be take AB and multiply by cosine minus sine, sine. And just because I promised this course to be completely self-contained, let's remind ourselves how to multiply vector by vector and vector by matrix. So if I have a vector V, which will be alpha 1, alpha 2, alpha 3, let's call it row vector. Another vector U, which is beta 1, beta 2, beta 3, then V dot product U is alpha 1, beta 1 plus alpha 2, beta 2 plus alpha 3, beta 3. And if I have more parameters, then I'll multiply them as well. And formally, I need to make sure that one vector is a row vector and another is a column vector. But since there is no source of confusion, in most cases, I will omit the transpose part that makes one a row between a row and a column. Okay, I'll just write U dot product V, which is a sum of the individual elements. Takes the first by the first, the second by the second, this times this, plus this times this. And if we are already mentioning it, it was mentioning that it has another expression, which is the length of U times the length of V times cosine theta, where theta here is the angle between U and V. Just for all to know. And if we are already here, it's worth mentioning that U dot product U for any vector U is equals to what? Alpha 1 square plus alpha 2 square plus alpha square, which is just the length of U square, just because of Pythagoras. Right? If I have a vector x, y, think about this point as a vector, think about the origin and where this vector is going to, then Pythagoras will tell me that take x square plus y square and take the square root of this number, you'll get the length L of this vector. Okay, hopefully I bore everybody in this part that you have seen it before. And next, if I have a matrix A, and I'll imagine this matrix as consists of vectors U1, U2, all the way up to UN. That is, it has n many rows. Of course, I can think about this matrix also as consists of columns, but I don't. This matrix will be A. And now I have another matrix, B. And this time, I will think about its elements as consist of columns. Think about V1 as the first column, V column, all the way up to Vn as the last one. And to make sense out of it, I'll make sure that let's call it M, because I already used N. of Vm. And to make sure out of it, I want to enforce that k, which is the length of these vectors, that is the number of columns in A, equals to the number of rows in B. K must be equal in K, otherwise what I'm going to describe is illegal. This is another matrix C, such that C at index I, comma j, C at index I, comma j is nothing but ui, the vector ui, dot product vj. Okay, so first, without any proof, if you bought that the transformation that I described earlier was a transformation of rotational by theta, then you should believe me that if you are applying my formula about multiplying the rows of this matrix, now theta takes the first row, multiplies by AB, takes the second row, multiply by NB, and this will spit out exactly A prime, B prime, the coordinates of this point. But there is much more into it, and we'll revisit it. Before I continue, let's describe the transformations that we already saw, but let's do scaling. Oh, let's play. Let's M be the matrix of a 2, 2, 0, 0. What does this matrix do to a point x, y? It takes x, y, it takes the vector x, y, and it sends it to 2x, 2y. If you're not sure, the vector 2, 0, the first row, times xy takes 2x plus, let's write it first in details. Take it into 2x plus 0 times y. This is this 0, 0 times y. And the second component would be 0 times x plus 2y, which is nothing but 2x, 2y. So this was our scaling. Let I be the following matrix: 1, 1, 0, 0. What is noticeable for this matrix 1, 1, 0, 0, also called the identity matrix, takes the identity matrix I and multiply it by any vector or multiply by any matrix, and you'll get nothing but U again. And if you multiply the identity matrix by a matrix M, you'll just get M back. And if you take the matrix M and multiply by the identity matrix, now the order is reversed, you still get M. Great. The inverse of a matrix A is a matrix B such that A dot product, the product of A and B, gives me the identity matrix. The inverse matrix of a matrix A is a new matrix B, such that A times B gives me the identity matrix. But if we are in dimension of 1 by 1, and matrix is just a scalar, then if this is A, then this B is just 1 over A. But if this is, if A is nothing but a scalar, alpha, then B, the inverse of A is 1 over A. Yeah, because so the product will give me 1. Identity matrix is just the 1 of matrix multiplication. And if I'm going now, when I told you what the inverse needs to do, I can also give it a more meaningful name. So instead of calling it B, I will denote it by A to the power of minus 1. Because A times A minus 1, if it exists, gives me I. And in general, those of you who took linear algebra knows usually when I'll show you a matrix and I ask what is the inverse of this matrix, you are doing Gauss elimination. It takes n cubed, diagonalization, reduce elements until you triangulate everything when 1/2 of the matrix, one triangle of this matrix, is 0, and then you can see if the inverse exists or not. Where do you see inverse a lot is if you are trying to solve a linear system of equations. Like linear algebra, you have a vector x of unknown, and you want to solve a linear system of equation, ax equal a new vector b, then an option is compute A inverse, if it exists, and now multiply both sides by A minus 1. So A minus 1 times A times x should be A minus 1 times B, and this this cancels this, so we are left with x equals A minus 1B in general. So that's how solving a linear system of equations and finding the inverse of the matrix are very much related to each other. So you can, in n cubed time, subtract and multiply various rows of the matrix until you are finding the inverse using Gauss elimination. Look at the matrix M right here. What is M minus 1? The inverse of M over here. Don't yell. Let's a question things with everybody. It's not a hard question, but and now the inverse doesn't always exist. Not for every matrix. You can find an inverse. We'll talk more about it. But and if it does exist, as I said, you can find it in algebraic methods. But now I want you to find the inverse of M, but with geometric method. Negative 1/2, I think that half and half, that M minus 1. Because let's meditate about M right here. And let's say that M takes this person. And what is M doing? We talked about it. It's scaling. It multiplies the x by 2 and multiplies the y by 2. If I would write 2 and a different number, then it just changes the aspect ratio. Maybe I multiply the x by 3 and the y by 2. So what does M do? It takes this person and move it more to the right and make this person twice, 2 times this guy's height. Now, what do I expect M to the minus 1 be? Remember, if to look at this person, pick a point P, the center of this person's head, M times P, sorry, restart. This is P, then the center of the head is in MP. That's the center of the head. What do I expect the inverse to do? Tell you, if I look at this vector and multiply it by m minus 1, that let's pretend that I still don't know, m minus 1 times m times p, then it doesn't matter where I put the parentheses. This is just equals to m minus 1 times m times p. Then I'll put the parentheses right here, which is nothing but p. That is, the inverse should make a transformation that will move this red point m times p to p, the original p. So I'm looking for a transformation that will cancel the zooming out by 2. That is, it's zooming in by half. This matrix just shrinks by half. Make sense? And of course, algebraically, let's verify it 0 time looking at this row times these columns gives me 2 times half plus 0 time, etc. Now, help me redraw this person once I multiply by m. Now it's a different m. Just reflection around the x-axis, right? This matrix times xy gives me x and minus y. That is reflection by the x-axis. Fair enough? Transform it to this person. And the inverse of this matrix? It's an own inverse. Just reflect twice. So this fine box, where does it go? Under this matrix. It's shearing, like this times xy takes x stays the same, but what happened to y? it's y plus x. So look at this point with some value of, let's ask, what happened to 0, 0? 0, 0 doesn't go anywhere, stays at 0, 0. Points fall on the y-axis. Point on the y-axis doesn't move at all because the x value is 0. Point on the y-axis means the y-axis is 0. But now I look at a point P and P prime, which is MP. What do I know about P prime? It will have the same x value as the original P, but its y value will increase by what was the x. We talked about it. That's just the shear transformation, shear by x. Okay, so how will the box looks like? After the transformation, it will look like a it will be a parallelogram. You have it nicely drawn in the slides before. The length of this edge is longer than the length of this edge, but D prime is the image of the point D. It has this D and D prime has the same x-axis, except that now I added the y. People, yeah.
Wait, so why would the length of the vertical edges be longer?
The length of the vertical edge, is this true what I said? I think it's not true. No, it's the same. Okay. Take it back. It's a parallelogram. The length of this guy and the length of this guy are the same. But it started as a rectangle, and now it's parallelogram. This angle is not 90. It's my attempt to draw attempt to draw it right here. Okay, let's go the opposite direction. This time you'll tell me what are the matrices that I want to generate. So I have the line L, which is the line L y equals ax, and I have this beautiful house over here, and I want to transform the house to reflect the house. So the house is reflected by the line L. Everything that lives above the line should be reflected. And everything below the line should be, everything below the line should be reflected to be above the line. And here, this angle is theta. And I don't ask you what is the matrix of this whole transformation. I want you to show me a few matrices that had I take the time to actually compute what is their product. It will be the transformation that I need. Again, I don't necessarily ask you what is the transformation as a single matrix. Give me a few matrices that if I'll multiply them by each other, I'll get the right transformation. So I'm asking you what is M, which would be M1, so write it, M3, times M2 times M1, the product of these three matrices. And I gave the indices, so this is M1, because if I'll now take M and multiply it by a point P, like the top of the house, then the order of operation, you can think about it as first multiply P by the first matrix, M1, and M1 should be one of the things that we already saw. Take the product, multiply it by M2, take the product, multiply it by M3, and if you did all of it, then this red point, the top of the house, if the top of the house before the transformation is P, then the top of the house after the transformation, P prime, should be MP, should be the top of the house after this product. So before we start with the matrices, algorithmically following the mathematician joke, what should I do? Three operations. Somebody else that we didn't talk today? Yeah. Bring the problem into a setting that we already know how to solve. Already know how to solve reflection by the x-axis. How would I do it here? We already saw this example. Rotate by minus theta, because it's rotating it's rotating clockwise. So M1 will have the job of rotating by minus theta. M2 should be the flipping, that is reflect by the x-axis. And M3 rotate clockwise. Rotate by plus theta. I'll highlight it. And if you implement something like this in JavaScript, and you will, when we'll play more with ray shooting, we'll give you a template that does matrix multiplication. So just for completeness, M1 would be what? Cosine minus sine, sine, cosine of minus theta. Now, the sine of sinus sweeps when it's minus theta instead of theta. The cosine doesn't care. M2. Help. This one. And M3 is what we just said, cosine, sine, cosine minus sine, sine and cosine, but of positive theta. And in equations like this, if you see it in the homework, in the theoretical part or the exams, usually I wouldn't ask what is actually the product. I just want you to see what's happening. In terms of how your computer should execute all these operations, your computer should compute what is a product of all these matrices, and maybe many more as a single matrix, and then push it into the graphical pipeline. Okay. Now, when we start to rank the painful topics of this course, the next one stands in a good place. When I'll ask you. So the next topic is homogeneous coordinates. Why do I tell you about homogeneous coordinates? Yeah. our computer, since with plenty of such points, what we expect the graphical pipeline, even with no GPU, with no anything, is first compute this product, because there is many more points than the complexity of just multiply a few matrices. That's extremely smaller, no matter how many transformation and how many pieces I have in my arms and fingers, and how it's just simple multiplication comparing to the multiple, many vertices of all the triangles that my graphical scenes contains. Okay. So what's wrong with homogeneous coordinates? Oh, sorry. Cartesian coordinates, xy, and z, nothing wrong with it. But multiplication by all these matrices, all the matrices that we have seen so far, has a very distinct feature. They are all linear transformation. And as linear transformation, look at all these matrices, multiply them by the vector 0, 0, and there is not much that you can do with it. The result will be 0, 0. The matrix translate, flip, shear, it will not move 0, 0 to any other place. And I need translation. And like translation, I need to introduce homogeneous coordinates. It's not the only reason. We'll also, at least in one other case, when we'll keep order for the z buffers to see what's closer than what. But they are extremely do all the transformation, including translation. And if I'll stay with Cartesian coordinates, only x and y, or in 3D only x, y, z, you will not be able to multiply a point by a matrix and shift this point by some amount. Okay, so I'll decide about the same point. The same point for which px equal 4, y equal 2. Here is p equals to 4, 2. And just maybe to make it less awkward, I can write the same point by specifying other parameters, like the distance from the origin and theta. I can write the location of this point in a few other ways. But so now I want to represent the location of this point using not 2 numbers, but by using 3. And the 3 numbers in homogeneous coordinates would be 3 numbers, x, y, and another one which is not z, and it's not time, it's not animation, nothing moving here, it's w. And when there is a chance of confusion, I'll write age right here to denote it. You need to think about the 3 numbers as 3 numbers in homogeneous coordinates. And when you see it this way, you can think about it as a point in the Cartesian plane and with values x, y in the Cartesian plane. And how do I know where this point P actually located? When I'll tell you about the 3 numbers, what you're going to do is to ask what is the x coordinate of P? What is really the x coordinate of P? You showed me 3 numbers, I want to know what's the x coordinate of P. It's not the first number necessarily, but it is take x and divide it by the last number, w. What would be the y value of the new point? Take the second number that you see over here. I called it y, but it's the second number, and divide by the last one. So to ask where is P, P is in the location x divided by w and y divided by w. And if we are living in this 3D world, then if I'll show you the point whose homogeneous coordinate are x, y, z, w, that's my z, by the way. That's in homogeneous coordinates. This is a point in 3D, but I wrote it using 4 numbers. Homogeneous coordinates. Where is it actually in 3D? In the Cartesian plane, it is in x divided by the last number, w, y divided by the last number, w, and z divided by the last number, which is w. That's in Cartesian coordinate. So notice in particular that now when I have 3 numbers to just represent something with 2 degrees of freedom, point have just x and y, but I can use 3 numbers, then this representation is not unique. For example, this point P that you see over there, 4, 2, I can write it in homogeneous coordinates as a triple 4, 2, and the last number is 1. Because x divided by 1 and y divided by 1 is just x and y. We didn't change. Still 4 and 2. But I can also write it as 8, 4, and 2. It's the same point. And remember, I'll tell you that it's in homogeneous coordinates. And where is this point located? It's 8 divided by 2, that's the x coordinate, making it 4, and 4 divided by 2, making it 2. I can also write it as 2, 1, and 0.5. Still the very same point. Right? Because 2 divided by 0.5, making it 4. Okay, so the very same point P, that's in Cartesian. And I can write it as, let's take the last one, 2, 1, and 0.5 in homogeneous coordinates. Now, when we are moving from Cartesian to homogeneous, usually what we'll do is just adding the 1 at the end. That is, usually the graphical pipeline will just convert everything to homogeneous coordinate by just adding the last number to be 1. Don't change x, don't change the y. Once it's 1, then dividing by 1 doesn't matter. Okay. In the list of confusing unfavorite points, I think that it's the first thing that looks quite awkward if it's the first time that you see it. Now, remember my big goal was to be able to express translation via matrix multiplication. Everybody is cool with the homogeneous coordinates? As much as you can be cool if that's the first time that you see. So once again, the 3 numbers are not the 3 coordinates of a point in the 3D world. It's 3 numbers that represent the location of a point in the 2D world. And when I want to know where is this point in the xy plane, take the first, divide by the last, that will give you the x. Take the second, divide by the last, it will give you the y. And if it's actually in the 3D world, then take the one in the denominator is always the last one, the w. I can define it in any dimension. The last number is always what you're dividing by. So if the point lives in 3D, then you are taking the third number and divide by the last one, by the w, and that gives you the z. There was a question?
So aside from enabling us to do translations, which is what I feel like this is very important for, why not restrict the homogeneous, the w operator to just 1? What's the point of not allowing w to equal 2 or 0.5 or anything else? It's either translating or it's not translating.
Because we will also use it when we'll look at points. Somebody can think about transformation that involve homogeneous coordinates? I didn't have to, but transformation from 3D to 2D. Where do we have transformation from 3D to 2D? Projection. Perspective projection, what do? When I have a point, we'll of course cover it, but if, as a promo, if this is my eye and I have a point whose location is x, y, I mean that x will be x will be the distance, y will be the height, my eye is at 0, 0, and I want to project it. I want to project it on my screen. And to project it on my screen, I want to compute a line that goes from my eye to this point. On which pixels will it fall? Again, a line from my eye to this D. I just used x, y because it's on the plane. But where will it appear? To which pixel will it be projected to? And for this, I need to take the distance, x, and take the y and divide by x. And that I can do is matrix multiplication. That will give me this value, y prime, the pixel, the height of this pixel that it falls to. Y prime is, just because of triangle similarity, this divided by this is, let's decide that this is 1, so I didn't expect this question. The screen, the distance of the screen for my eye is 1. So this divided by this is divided by 1, which is just 1 y prime. That's a pixel that it falls to. So y prime equals to y over x. Right. Y prime divided by 1, the distance from y, is y prime divided by x. And if I'll project and make x the last number that will appear, then I got a point in 2D in homogeneous coordinates. That's another example. That will not be surprising. What will be surprising is that I can do it and even reconstruct the order between them, so I know which one is closer to which the Z buffer algorithm needs to know if it changed the colors or not. But that's all waiting for us. Okay. Look at the following matrix. 1, 1, 1, identity matrix. And I'll tell you about an input, x, y. And since I have control on the input, I need it in homogeneous coordinates, but I can decide for the same ways. I'll pick the simplest one, which is just makes the last number, the WB, 1, in the input. What about the transformation matrix? It is identity, except that the last column, instead of 0, 0, it has two other numbers, alpha and beta, that I have in mind. What the result of the product of this times this? The first number which you are generating by taking this row times this column, is x0 times 1, x0 times 1, plus 0 times y0, plus alpha times this red 1 that you have over here. So the first coordinate is x0 plus alpha. Alpha is this number that I wrote here in the corner, no matter what is alpha. And no matter, so I took x0 and added alpha to it. Which transformation did it do? It shifted the whole plane by alpha to the right. What about the y value? The y value at the output would be, take the second row, which was what? Identity, except that the last element I changed to be some other number, fixed number, beta. Fixed meaning it doesn't depend on what is the input point that I have. Beta. And this row times x by 1 will be what? 0 times x0 doesn't contribute. 1 times y0, making it y0. The same, so the y of the input is also the y of the output, except that the beta times 1, just add another beta over here. What about the last coordinate, the w? 0, 0, 1 times x0, y0, 1 just gives me 1 at the end. So what happens? The point xy moves to the point x plus alpha, y plus beta. So if I decided that I want a shift of the plane by 2 units to the right and 3 units downward, I'll set it to be 2 units to the right, alpha will be 2, and beta will be minus 3, reduced by minus 3, yeah.
What would like rotating by theta with homogeneous coordinates?
Excellent question. So we had all the friendly transformations that didn't need homogeneous coordinates, and they were written as a 2 by 2 matrix. I'll make it a bit larger, sorry. All the friendly transformation except the translation were written as a 2 by 2 matrix. For example, cosine minus sine, sine and cosine was of theta, was a matrix that we used for the rotation. Now I need to make it applicable to homogeneous coordinates. All I'll do is write 0, 0, 1, 0, 0. So that's true for the rotation, that's true for the flipping, that's true for all the coordinates that you have in mind. So these are my 3 columns. I just pad it with 0, except it's the last number. I set it to 1.
Other question, why can't we use like the W for scaling?
No reason. It's not unique. It's definitely not unique. That is the same point I can write in multiple ways, and now I have more degrees in the transformation. I'm not saying any point that that's the only matrix that will do this translation. But that's the simplest, at least that I can think of. And usually when you want to do shifting, you'll see the shifting by take this 2 by 2 matrix, and if you'll take the last column and replace the last column, it's a bit, you don't have to remember it, but if you're making the last column instead of 0, 0, 1, alpha, beta, 1, you're getting also the shifting effect, no matter what happens here. Okay, so now we can rotate the house around the point C. You have the house C, you want to rotate the whole house. How would you do it? What does this matrix does for us? Remember, the input I took all the points x, y, and I move it to be x, y, 1 as the last number. It's only on homogeneous coordinates. So take a point P, multiply it by this matrix. What will be the effect? Does this matrix shifting by minus C. Notice minus x0, minus y0. Also notice the order. The order of multiplication is from right to left. We multiply it from the right. By the way, the text in graphics, you might find it either multiplication from the right or from the left. It's not universal. Okay? But in these slides, I'm multiplying from the right. That is, P will come from the right. P times this matrix takes C, shift it to 0, 0, takes this corner and shift it by minus C, takes this corner, shift by minus C, etc. That answers the rotation matrix. As we said, it's an old 2 by 2 matrix of the rotation. plus the 1 over here. That is just to keep it all legal for the multiplication. And this matrix does a shifting by plus C. If I started by shifting by minus C, now I'm shifting everything to by plus C. And theta here is a negative, is a negative angle to make it consistent with the slide.
I was going to ask about that, because why is it negative theta, but I feel like the middle matrix is a positive theta.
Well, I rotate by minus C. I rotate by minus theta. So, theta is a negative value. Yeah, I can write with it. Here it looks like it's rotating by theta. So yeah, I should have said that I'm rotating around the origin by theta, but theta is negative to make it in this slide.
Okay, so they don't match up.
Correct. Thanks. Yeah. Accept the correction. So theta, it's rotated around by theta, but theta is negative. Okay. Same question as before. What is the inverse of this matrix? You can do Gauss elimination, or use geometry and
Just negative alpha, negative beta.
the same, except that you write minus alpha and minus beta. That's the inverse, because if you moved it by one step to the right, now you move it by one step to the left. That's how you're generating the identity. Okay, I want to go back to the rotation. Why? Because I want to show you how it's consistent with writing things using complex number. If you know complex numbers, not mandatory. If you don't, maybe this slide will confuse more than it helps, then ignore it. More importantly, I want to show you how to switch from one coordinate system to another, and that's not necessary when we live in 2D, but is extremely helpful when we are living in 3D. Because rotation in 3D will be very, very common when you're saying, here is my camera, but I'm watching in this direction, and this direction is up and this direction is to the left. How do I rotate points from wherever inputs are given into the coordinate system that the camera sees? Then the next slide will be very helpful. But first with complex numbers. So if I have two complex numbers, remember, if you know one complex number, Z1, have a real part, x1, plus I is square root of minus 1. I is a square root of minus 1, in the sense that I square equals minus 1. Just to agree. So now, the same goes for Z2, x2 plus extra y2. Now, when you're multiplying two complex numbers, I can represent these complex numbers, Z1 and Z2. I can ask for each one of them, what is the angle that you create? The angle, or the argument, is this angle, the angle that it creates with a positive x-axis. So that would be alpha 1, did I give it a number? Alpha 1, that would be alpha 2. What happens when I multiply two numbers, two complex numbers? Then the argument, the length of this vector, how far away the points are from the axis, Z1 times Z2. If the length of this guy is 3, the length of this guy is 2, then Z1 times Z2, its distance from the origin will be 6, and it's probably not exactly here. Why 6? Because it takes the length of Z1 times the length of Z2. What is the angle that it creates? What is this angle that it creates? It is alpha 1 plus alpha 2. That's one way to do multiplication. Another way to think about the multiplication is, this drawing starts to be crowded, is if this point P, if this point Z1, I'll write it as x1, its real value is x1, I, y1. And Z2 equals to its x2 plus I, y2, like it is in the slide. And now let's do the product. Multiply this by this, and don't forget that I times I equals minus 1. So what happened when I multiply them? Z1 times Z2 equals to x, just like normal, what you're doing when you did in school, alpha plus beta times gamma plus delta. What did you do? Alpha times gamma plus alpha times delta plus beta times each one of the pairs. It has a name which I don't remember. So it will be x1 times x2 plus y1 times y2 times I, making it minus 1. So minus y1, y2. That's a real number. The piece that doesn't contain I. What about the piece that does contain I? It will be I times x1, y2, and x2, y1. The real of one times the imaginary of the other. Now, after all this long discussion, let's decide that Z2, here is Z1, one of the points. Every point I can just look at the xy and decide, hey, from now on you're not a point, you're a complex number, and your xy are just a real and imaginary part of a complex number. But now I want to multiply it by the following complex numbers, which will be Z2, which is cosine theta. So its x value is cosine theta, and its imaginary, its y value, I sinus theta. What is the length of this number? What is its absolute value? How far away is this from the origin? 1, because cosine square plus sinus square equals 1. Pythagoras. But this square plus this square equals 1. So when I do the product, I never change. When I look at Z1 dot Z2, the length of them, the length of this guy is just the length of Z1. Z1 is going to be any of the points in my input. Now, as you remember, what happens when I look at a product? The new angle is the old angle rotated, which will make sense with all the equations that we have seen so far, because when I'll do the product, it will be what? The x coordinate of x2, the x coordinate of Z1 times the x coordinate of Z2, which is cosine theta, minus the y coordinate of Z1 times the sinus theta, which is exactly what I expected. Because what am I doing by multiplying by this complex number? I rotate everything by theta. So cosine theta minus sinus theta, cosine theta minus sinus theta, that's what happened to the x. And here is what happens to the y. the y will be x sinus theta, the x of the point sinus theta, plus the y of the whole point cosine theta. So at least it's consistent. Okay, and the idea that you can rotate by multiplying will be useful when we'll talk about quadrillions, which is a very mysterious thing that is extremely useful in 3D rotations. It's actually useful in gyroscopes of MacBooks. I know that they try to decide, resolve, did it fall and how is this rotated, and so on. And we'll see how, again, visiting rotations as moving from one coordinate system to another. That one trick that will help me do rotation would be to say, hey, I want to rotate this point A, this point C, and to rotate this point C, I'll ask, hey, a vector that was oriented with the x. After the rotation, it will be rotated to some new vector. Let's consider its coordinate. A vector, unit vector that was directed with a y. After rotation, here are its new coordinates. And now for every point C, I just want to generate a vector that will multiply this and this somehow. Why is this all useful? Because if I have, it's not too useful for two vectors. When I have three vectors, suddenly what you'll see is that all I need to do, you have one vector that points from the camera somewhere. You have one vector that points from the camera to the left or up. All you need to do is the rotation matrix that you'll need is just take these three vectors, u, v, w, and write them as column vectors. And miraculously, it will do the trick for us. Okay, enough. Questions? So we have to finish it and move to new topics. Thank you.